Okay, so I think everything's working. If somebody in the chat can give me some indication if the stream's up and working, it'd be great. I always sit here wondering if it's working. So I'm going to start off with emailed questions. And the first email came from Will. Thank you for the email. It was very nice of you. Yeah. He says, could you please quickly go over what the differences are between acid and base reactions and the acid and carbonate reactions are? I'm just unsure how to distinguish which is which. So, thanks Troy for giving me a notification that the stream's working. So hopefully I don't disappear off the webcam. There we go. So for acid and base reactions, that's going to be things like hydrochloric acid or nitric acid or vinegar, stuff like that. And they all tend to have this hydrogen part of their molecule, and it's a special hydrogen because it actually is weakly attached. So when hydrochloric acid is put into water, it actually splits apart into its separate ions. So you'll get a H plus ion. I'll just make that little circle there. So it floats around in the water, separated. And the chloride ion, which is the other half of the molecule, it starts to float around in its own solution. So acids tend to make these H plus ions. You can see that there's a hydrogen here in the nitric acid formula. And there's other acids which I think I mentioned in the notes, so I won't go over them. When you have a base, so a base is something that will accept these hydrogen ions. And that most commonly I find that simple high school bases for high school chemistry, you tend to find formulas that contain this OH group, particularly attached to a metal. Okay, that makes it easily, it comes off. If you find the OH is attached to something more like carbon and things like that, not really likely to pop off. So this one here will break off into a sodium ion, so Na+, and it'll split apart into OH-. And it's this OH- which can bind up with the hydrogen near and make water. So if I've got the two put together, so HCl, my acid, and I add it with a base, so sodium hydroxide. And the reason why I'm always using these two examples is that they're like it is the typical example of an acid and a base. So any textbook, 9 out of 10 times you'll see that their typical example of an acid-base reaction is specifically these two things here. Probably because they're very common, or probably because they're very simple in terms of their chemical makeup. So it's not a really long formula, it's not very complicated looking and so on. So if I add these two together, I'm going to get some products. So this hydrogen will pop off, this OH will pop off, and those two parts can come together. So you can see a plus ion and a negative ion here. These can pair together. What will I get? H and OH. That gives me two H's, doesn't it? So H2. And I have an oxygen as well, which gives me H2O. So it's water. What's left remaining? It's going to be the other bits. So the chloride ion is still left behind, and the sodium ion is still left behind. So those things can pair together. So in fact, it works. Because sodium is positive and chloride is negative, we know opposite charges attract, so they'll go together. So I'll get that, and I'll get the sodium chloride. So what's going on here? Basically, we have our acid plus base produces water plus salt. And this occasion here, NaCl, sodium chloride, is actually common table salt. You can get different kinds of salts depending what metals and non-metals you pair together. So you can have magnesium chloride, you can have aluminium chloride, you can have other kinds of things. You can have potassium iodide. These are all salts. Okay, it's a sort of a common word. Right, so that is what an acid-base type reaction looks like. For acid carbonate, well, I've already defined what an acid is. Let's look at what carbonate. Carbonates is any compound, so usually there's a front half to the formula, and then on the end of it you'll find this part Okay, this part here is called a carbonate ion. Typically, if you were just to write in its, I'll leave that till later. So anything with a carbonate attached on the very end of its formula, so CO3, and I was giving notes in class where you have this sort of naming structure. If you can see ATE on the end of it, that's kind of like the word eat. Is that? Can you sort of see that in the video? That's as far as it zooms in. I'm sorry, guys. Eat. Can you see? Yeah. So it looks like the word eat. So carbon has eaten, and it has lots of oxygens on it. So I was giving a point there when you see carbonate or sulfate or the other eights, phosphate, they tend to have gobbled up quite a lot more oxygens than typically. So I hope that helps you sort of pick it out or remember what it looks like when you see it. Let me just focus the camera again. Trying to keep up with the... Hey, Jasper's here. Jasper, what are you doing here? This is Year 9 stuff. Okay, acid and carbonate, so that'll be things like I'll have the hydrochloric acid again, so HCl, and I'm going to use a relatively simple carbonate compound, so I'm going to use calcium carbonate. Calcium is a 2+ ion, carbonate is a 2- ion, so they pair together in a 1-to-1 ratio. So what's going to happen? Well, I'm actually going to need 2 lots of this, so I'm going to put a 2 here for now. Basically, the carbonate compound will behave like a hydrogen acceptor, so it's technically a base. It's not a strong base. Tends to be quite weak, and I'm not going to go into details what makes something strong or weak. Yeah, leave that to grade 11 and 12 chemistry. But it'll basically absorb those hydrogen ions that this acid here produces. And when it does so, you'll basically replace this calcium ion with those hydrogen ions. And so you'll have you'll have an intermediary chemical. I won't write it down because I thought that people in class found that part confusing when I gave you the middle step. But basically, it will absorb it, and then that intermediary chemical will break down. And when it breaks down, it'll create gas. It'll create carbon dioxide gas. So you'll get CO2 gas. You'll always get water whenever you have a chemical, whenever you have a reaction with acid something. Well, not always, but you know, most of the time when you have acid something reactions, you'll tend to make water or salt. In this occasion here, we'll make water and salt. So I will get a salt compound made out of calcium and 2 lots of chloride. So what's the general format here? We have acid, so that bit there is an acid. We have our carbonate. And that makes carbon dioxide and water and salt. That's the general form of an acid carbonate reaction. And if you actually memorize these, it helps you sort of predict things. So if I gave you a different kind of acid, so if we swap this out from HCl, if I swapped it out for nitric acid, HNO3, I'm sure that you guys could sort of fit it into this format and predict what the salt will be. So if that's the case, let's just do one now, since I'm not really getting any questions. Oh, I do have a question. Do you have questions? Okay, so Digital Gamers asks, do we need to know how to balance chemical equations? On this particular test, not as much. Any other questions? Who is Digital Gamers? Don't know. All right, so back what I was saying here is that now we have a template here to work with. Acid plus carbonate will give you carbon dioxide, water, and salt. I can basically swap out the acid for any acid, and it should basically work out. So if I've got nitric acid, it brings 1 H+ ion, and if I pair that together with let's say, a different carbonate compound. So I'm going to go with sodium carbonate, Na2CO3. Slightly different from what we used in class. We use sodium hydrocarbonate. Here I'm writing sodium bicarbonate, bi meaning 2, so it's got 2 sodiums on it. What am I going to get? I should get some carbon dioxide, so here's my carbon dioxide. I should get some water, so I'll get water. And I should get some salt. What is the salt going to be? Well, the salt's going to be the leftovers. So I've used my hydrogen, it's been absorbed. I've used my carbon and oxygens here. I've got some nitrate, that's NO3, that little anion there. You won't need to memorize, nitrate, sulfate, phosphate, carbonate. You don't have to memorize all of them just yet. We will sort of leave that for you to memorize in grade 10. But I happen to know that this is called a nitrate compound. This piece here will pair together with the sodium ions from here, so I will get sodium nitrate. And then from here onwards, you basically balance the equations. So you put in the coefficients front and so on. I'm not going to do them now. Generally get them wrong when I'm doing on the fly in a hurry. Do we have any other questions? I hope that sort of answers Will's question, where the two things are just slightly different. Acid-base reactions, you'll get water and salt. Acid-carbonate reactions, you'll get water and salt and carbon dioxide gas. I guess that's another way of sort of looking for differences. If there's no questions in the chat feed, I might just prattle off a little bit more about graphs and data analysis. So something I'd like to talk about. Yeah, and I figured, despite the survey, what time of the evening works best for everybody is for the live stream. I figured there'd be some people who were interested, but I think most people were pretty satisfied. Most of the questions and worries were answered during class time, so fair enough. And not many people could make it. I think only like a third of people actually could make this time slot. Right, so I was going to talk about some data analysis. So there's a thing called anomalies. Or outliers. Okay. I'm sure that they have specific meanings to differentiate which one is which. But for now, my memories, they're roughly the same thing, and for most occasions, it doesn't really matter. So if you say anomaly or if you say outlier, I think it's fine. For at least for year 9, it's fine. But you tend to find anomalies in data tables. So when you collect the raw numbers, you might find outliers in there. You might also find them in graphs, and they may not be visible unless you look at your numbers in form of a graph. So if I write out a set of data, so let's say I'm collecting some numbers, so 12, 15, 16, 14, 10, 15, and I don't know, 16 again. So from this selection of data, it could be anything, it could be how many points you scored in the last game, or it could be how many minutes you're able to survive in the computer game before you got, knocked out of competition. Doesn't matter. Each of these data points can refer to a different trial. So a trial where you're trying to repeat. So let's say I was trying to do the computer game. I was trying to measure what's the average time I survive. Well, my wife, technically, because she plays like Overwatch, and each round, obviously you respawn. So maybe you can sort of count how many minutes it is until you get shot and you have to respawn. So each time you have to respawn, it gives you a new data point. So you're sort of testing yourself, same conditions, so the same game, same opponents. Each time you do the game, respawn, sorry, you'll get a different, recording of how long you survive. If I was to look at, I'm going to try and analyze this data, is there anything here that doesn't seem like it belongs like the rest of the data? Okay, In that case, it would be this number here. 10 is quite far away from the other data points here. You might think, oh, but it's really important to count every single piece of data. It's like, well, to some extent that's true, but sometimes you'll have one recording which can be really far off the mark, and that's just because some things, life happens. For example, if I'm trying to measure how long it takes you to run the 100 meters, and I'm timing you, and I'm getting you to do it over and over and over again, maybe one of those attempts, mum calls you on the mobile phone, and then you have to stop in the middle of the test, and you're sort of answering your phone, and meanwhile the timer is ticking, and then you finally finish, like, leave me alone, mum, and then you put down your phone, then you finally finish your 100 meter, and then I say, geez, that took a really long time. Is that fair to count that in my results? Not really. It's not an accurate, it's not a realistic, it's not a fair representation of the data. Like, I want to figure out, when you do your 100-meter sprint, how long does it take you to do it? I don't want to count how long it takes you to do it when sometimes mum calls you on the phone. That's not part of my test. Whose phase? I don't know. Phase sometimes shows up. So this one here I would call an outlier. And when you have outliers or anomalies, the thing you do with them is you point them out. So usually you cross them out, or you highlight them and make a note somewhere in your report that this has been identified to not belong. It seems odd compared to the rest of the grouping. And what do you do from there? Well, basically any calculations you need to make, so if you're doing averages or something like that, any further processing on this data, you need to remove that from consideration. So if I need to then calculate the average, I would calculate average of the data without this outlier, okay? I need to sort of forget that it's there and do my working based upon the rest of the data, which is good. So I would do the average of 12 plus 15 plus 16 plus 14 plus 15 again plus 16, all divided by how many test results I have. So 1, 2, 3, 4, 5, 6. And then whatever that magical number ends up being, I'm not going to do that in real time on the video, but that's the idea with anomalies and outliers. So you can sometimes see them in your raw data. Sometimes you won't see them until you graph it. So if I'm doing a test, I don't know, let's say I got time and I've got, I don't know, money. Okay, so how much money you are earning over time. So we're going from, start and then towards the end of this time that I'm measuring. And let's say I'm measuring it, let's say it's stock market, perhaps, stock market price. You might see a spike. Okay, you can see that overall, most of this graph of data tends to follow a shape that somewhat resembles this. Okay, if you were to sort of squint our eyes a little bit, blur a little bit, smooth it together, you would see that this kind of resembles this, plus this spike in the middle. What is that spike? Does that belong? Is that what's going on here? I would call that also as an anomaly or an outlier, because it doesn't seem like it belongs with the rest of the data. And then you might then have to talk about, why did you get this? Okay, maybe this is the moment where there was a sale on something, and then suddenly more people bought the item, and therefore the value went up, or something like that. Now that could be some sort of reasoning there. So outliers and anomalies, basically you can find them in data form, where they look really far away from the rest of the grouping, or they look like they're really far out of nowhere in your graph. If that's the case, you sort of have to pretend it doesn't exist and continue working. I'm going to check in with the chat feed if there's questions. Are you going to send us a link so we can watch this later? So we'll, as soon as I finish this session, as soon as I cut the recording, YouTube then basically sits on it for a while. From my end, from the channel controls, it actually goes into some processing. So it tends to sort of take that data and then tries to, I don't know, convert format, and then it finally shows up on the channel. So it may not show immediately. It might show up on the channel, I don't know, 5-10 minutes later. Everybody squinted. Lovely. I appreciate how everyone's following along with my squinting. Next thing I wanted to talk about in live stream, again, I'll cover this again in class, but if you hear it multiple times from different ways, it should stick better, I think. Last thing I want to talk about, which was describing graphs. I sort of just started on it before the lunch bell went off. So if you're left hanging and you're really worried, then this is what I was trying to get at. So when you have, I'm going to do a few graphs. So we had that one. I can make up something else, so like another one there. Then let's say, question, have you guys covered periodic functions? That'll be things like sine, cos, tan. Have you dealt with them in graph form? So if Will or Jamie can answer that one. I'll wait for you guys to answer if you do. I'm going to do this verbally, but you would write this by hand. But when you got some data, you're supposed to describe it, and then later on you would go into details to explain it or do some further thinking or analysis. So if I'm going to describe this graph, one of the simplest things I can do is you can describe its shape. Okay, so if you're purely looking at shapes of graphs, you can see how this one's got a bit of jagginess, all right? So you don't use the word jagged. You might say has some fluctuations in the data points, or has some variability. Okay, these are fancy words, so I'll put them. Variability. So it varies a little bit, or you might say fluctuates. Okay. You can see that it tends to fluctuate a little bit, but overall, you can see how it seems to start off around the middle, and then it starts to curve downwards. All right, that's the shape. Here we can see this graph here. Its shape is very much where it starts off very gentle, and then the graph becomes rises very quickly. It starts to rise quicker and quicker and quicker. Okay, you might recognize this as an exponential curve. Exponential curves tend to have this particular shape. And this last one over here, let me just scoot over the, can I zoom in any better? Maybe it's just better if I hold it up closer. May as well. This one here, when we're describing its shape, I would say that it starts off pretty rapid. Starts off at a low value here, it goes up quite rapidly, and then starts to taper off, or it starts to plateau. All right, a plateau is a geological, I think I can spell it right. So a plateau is a geological feature. So if you got like a hill and then it just sort of sits off flat, I think that's called a plateau. Never seen one in real life, but supposedly it's a thing. So that's just describing its shape. And if you were to go further into describing for detail, you could say, all right, well, what value do we start at and what value do we finish at? Okay, so if I'm saying for this middle graph that it starts off low, gently climbs, and then starts to rise more rapidly towards the end, you could say, well, if this is money, okay, and let's say this is, you know, 10, 20, 30, $40, okay, and this, let's say this bottom axis here is time, and I can say this is 0 minutes, 2 minutes, 4 minutes, 6 minutes, 8 minutes. I could go into detail here. So I could say this particular graph starts off at $10 at 0 minutes, gently climbs up to, I don't know, maybe $15 at 3 minutes, then rapidly rises more and more towards the end. So between 3 minutes and 8 minutes, you could say that it climbs a lot more rapidly. And it goes from the $15 mark to possibly, I don't know, $50 at the end. Okay, so I'm mentioning its shape. So it starts off low, goes up high. I'm mentioning what value it starts off at on this axis, at which point on this axis. So I'm saying it starts off at $10, so here it is here, at 0 minutes. Then I say, then it slowly climbs, so I'm telling which way it's going, so it's going up, slowly rises up to $15, so I'm telling you what value it is here, at 3 minutes, this bit here. And then same process, and then you keep stepping it through. So if you've got a graph that has, I don't know, different stages, then you could break it up into different stages. So if I have some data that does this for a while, then it does this for a while, and then it does this for a while, you could probably break it up into sort of this section here where it tends to just vary a little bit, but mostly overall the same value. So let me just, it's a graph, if that wasn't clear. You could say it varies a little bit for a while, and then at this point in time, it quickly rises to a high amount, then comes down to this amount, and then tends to vary again towards the end. So you might break it up when you describe it. I hope this helps, guys. We will do some worksheets tomorrow, and I've got them printed out. Beautiful color. It should be relatively straightforward. In summary, we have our acid-base reactions. Acid-base gives you water and salt. Acid-carbonate reactions. Carbonate is any compound that has carbonate on the end of it, CO3. So I could have calcium carbonate, or I could have sodium carbonate, I could have aluminium carbonate, I could have blah, blah, blah. If you have acid and carbonate reactions, you'll get carbon dioxide, water, and salt. We then talked about anomalies or outliers. You can find them in the table of results. So if you're collecting raw data, you can find sometimes a data point that's very different from the rest. That's an outlier. What you do is you sort of cross it out and forget that it's there, and then you proceed as if it doesn't exist. So you do all your calculations, you do all your estimations, you do all your references based on everything else. So here I did my average with, then you might see visually it's an outlier. And you might have to explain what happened there. Okay, you should usually follow up. Identify your outliers, and then you might have to say something about them later. And lastly, we looked at describing data. So you can describe the shape of the graphs. And we talked about, you can then mention the numbers. So it starts off at this value, then it goes to here, and then it's risen up to this value, and then it's risen up to here when it reaches this value, and so on. I'll leave it there for now. Is there any last questions before I hang up the live stream? So let me just check. People still squinting. Do we need to know the different types of reactions like combination or decomposition reactions? It's good to know, but focus more on your acids type reactions. So anything with an acid in it, focus on that because it's very similar to the experiment that we did. You'll notice that these are not combination reactions, they're not decomposition reactions. So here I've got two things creates two more things. So I'm not combining them into one, I'm not taking one thing and breaking it apart into two. So it doesn't tend to fit any of the other type of reactions. But they're good to know so that you can spot them next to you when you get to grade 10. So combustion reactions, decomposition reactions, corrosion, combustion, etc. Okay, I don't think we have any questions left, so I will end the live stream here. Hope you guys enjoyed it. I hope the new format where my face is over here and the and the table is over here. I might pick a bigger pen next time so you can see it a bit easier, but I'll see you in class. Thanks, guys.